In the previous lessons, I introduced the basic I/O model to you, and we saw how to analyze algorithms in this model, and we looked at the difference between cache-aware and cache-oblivious algorithms. In this lesson, I'm going to introduce the matrix transposition problem to you, and then in the following lessons, we're first going to develop a cache-aware algorithm for this problem, and then a cache-oblivious algorithm. Okay, so let's have a look at what this matrix transposition problem actually is. Remember that the transpose of a matrix is simply, well, it's the same matrix, but at the element at position I, j should be swapped with the element at position j, I. Okay, so the problem we have is as input we get this matrix, a two-dimensional array, and what we have to do is simply swap all the elements. So here in the picture you see the elements 1, 4 and 4, 1, and they have to be swapped, right? And that holds for all elements ij. It has to be swapped with j, I. So let's look at the setting that we have. Our matrix has size m times m, so n, the total size, is m times m. The matrix is, well, let's say it's stored in row major order, right? So blocks are formed row by row. And let's also assume that this is a very large matrix that does not fit into the internal memory. And in particular, not even one complete row or column would fit into the main memory. Okay, so now let's have a look at a very simple, almost trivial algorithm to compute this transpose. Okay, we simply go over the array in the following order, right? Essentially row by row. And whenever we come to a new item, then we're going to swap it with the place where it has to go, right? So I, j has to be swapped with j, I. So when we get here, for instance, then the red and the blue element have to be swapped. Okay, and we simply continue. We go over the whole array like that, and at the end, we've swapped all the elements in the one part of the matrix with the elements in the opposite part. Okay, this is a very simple algorithm, and probably the one that you would write if you had to write an algorithm for this. But now let's look at its I/O behavior. Okay, so what is the number of I/Os of this algorithm? Well, first we have to know how the blocks are formed, and we assume that it was stored in row major order. So this is the order you see here in which the blocks are formed. Okay, now if you look at how we scan over this part of the matrix, well, that's perfect, because here we also scan in row major order. Okay, so that's nice, because if it's stored in row major order and we also scan in row major order, then every block is read once, so the total number of I/Os is going to be n divided by b. But now let's look at what we do on the opposite side, right? Because as we scan over the matrix row by row, right? If we look at a, j, I instead of a, I, j, actually in that part of the matrix, we're scanning column by column. But that's going to be bad, because if it's stored row by row and we scan column by column, well then, if it doesn't fit in the internal memory, we're going to do one I/O each time. So the conclusion is that this sort of obvious, straightforward algorithm is not very good. It's going to need n I/Os. So in the next lessons, we're going to look at cache-aware, and after that cache-oblivious algorithms that solve exactly the same problem, but using only n divided by b I/Os.